Hi everybody, Justin here from chemistrynotes.com, and today we are starting a brand new section. This is kind of like a brand new chapter. It's section 17, Electrochemistry. So when you just by looking at the word electrochemistry, you know we're going to talk about the interchange or the interaction between something electrical and something chemical. And as we get further along in this section, we will see that that is absolutely true. So let's get started. This is section 17, electrochemistry. First of all, the definition of electrochemistry, because we haven't seen this term in any of the previous 16 sections. Electrochemistry is the study of the interchange of chemical and electrical energy. Now, electrochemical reactions or electrochemistry involves oxidation-reduction reactions. So this entire section, section 17, is going to focus on redox reactions. And when we have a redox reaction and when we have something called an electrochemical cell, which we'll get to, two things can happen. There's a number 1 here, and there's going to be a number 2 here. Number 1 is by far our primary focus in this section, but there are two things that can happen. Number 1, generation of electricity from a spontaneous chemical reaction. So a spontaneous chemical reaction can be used to generate electricity. Or number 2, we can use electricity to produce a non-spontaneous chemical reaction that wouldn't typically go on its own. Remember from section 16, a non-spontaneous reaction isn't going to occur naturally on its own without some sort of outside help. And that outside help in number 2 would be electrical energy. All right, so let's move to the top of page 2 of today's notes, and let's kind of break down a typical redox reaction. Now, we'll have a better breakdown later on and a better way to approach these things later on, but for right now, let's just kind of take a bird's eye view of a typical redox reaction. So we first introduced redox reactions in section 4 when we were talking about oxidation states and how to assign oxidation numbers. But here is a typical redox reaction. 8H plus MnO4 minus plus 5Fe2 plus yields Mn2 plus 5Fe3 plus 4H2O. So all those little bubbled charges, plus and minus, those are the oxidation numbers or oxidation states that we learned about in section 4. So if I see Fe2 plus going to Fe3 plus, I know this is oxidation because oil. Oxidation is loss. Loss of what? Loss of electrons. And then if I look at the Mn, he goes from plus 7 all the way down to plus 2 oxidation state. So the Mn is Rig. Reduction is gain of electrons. So the oxidizing agent is the one that gets reduced, if you remember from section 4. So the oxidizing agent is MnO4 permanganate, because permanganate, MnO4 minus, is getting reduced. Who's getting oxidized? Well, Fe2 plus is. If Fe2 plus is getting oxidized, he must be the reducing agent. See, the MnO4 minus is getting reduced. He is responsible for Fe2 plus getting oxidized. That's why MnO4 minus, who gets reduced, is the oxidizing agent. And then the same argument for Fe2 plus. Okay, you see the little star down there at the bottom of the page of our notes? It says redox reactions can be broken down into 2 half reactions. So the reduction is 8H plus MnO4 minus plus 5 electrons yields Mn2 plus 4H2O. The oxidation half reaction is much simpler. Fe2 plus yields Fe3 plus an electron. However, I have to multiply the oxidation through by 5 because I want my 5 electrons on the right to eventually cancel with my 5 electrons on the left. More on this later. This is not how we're going to approach half reactions and redox reactions. That was just a kind of overview of a redox reaction that we kind of learned about a little bit in section 4. Okay, we'll have a much better systematic approach later on in section 17. So I have a question for you, the top of our next page of notes. It says, so how does a redox reaction generate electricity? Well, to do that, we have to keep the oxidation and the reduction separate. We have to somehow separate them into two compartments. And so, how does a redox reaction generate electricity? In the previous example, if MnO4- and Fe2+ are present together in the same solution, kind of like in the same compartment or the same flask or the same solution, they're just there together, the 5 electrons that are transferred directly upon, they would be transferred directly upon collision, and that's no good, because that means the electron transfer, the energy produced from that would just be lost as heat. We want to somehow harness that 5 electron transfer. So it says in the little bullet point there, this is not productive because the energy generated is lost as heat. So if the 5 electrons are transferred directly upon collision, that's no good because it's not productive and the energy generated would be lost as heat. So instead, in the second bullet point there, it says instead we must separate the oxidizing agent, MnO4-, and the reducing agent, Fe2+. If we separate them, give them their own compartment, then we can somehow harness this 5 electron transfer. All right, so this separation, it says, okay, so you got the second bullet point there, it says, so instead we must separate the oxidizing agent, MnO4-, and the reducing agent, Fe2+. This separation, so if we actually are able to separate the two, this separation forces the electron transfer from reducing agent, Fe2+, to the oxidizing agent, MnO4-, to occur through a wire. All right? Now why is that such a good thing? Well, if the electron transfer occurs through a wire, then we can take the wire and it can be directed through or towards a motor, and then the motor can be used to do useful work. So just to summarize, this separation forces the electron transfer to occur through a wire. The wire can then be directed through a motor to provide useful work. So we can use a spontaneous chemical reaction to provide us with an electrical output. Okay? That's very useful. So at the top of our next page of notes, let's talk more about how exactly we separate the oxidizing agent and the reducing agent. In other words, how do we have the reduction and the oxidation occurring together but separately? Because we need one to do the other, but then again, we have to have them in separate compartments. To do that, we use something called a galvanic cell. Sometimes they're referred to as electrochemical cells. So be patient with me here as I'm going to try to sketch this out. It says, separating the oxidizing agent and reducing agent. This is done by using a galvanic cell. And a galvanic cell is often referred to as an electrochemical cell. So I'm going to try to sketch a galvanic cell for you here. First, let me define. Galvanic cell is a device in which chemical energy from a spontaneous chemical reaction, spontaneous redox reaction, is changed to electrical energy. So I know my sketch is coming. I told you I was going to do a sketch, and I should be able to do it here after I define galvanic cell for you. So galvanic cell, just really quick, a device in which chemical energy from a spontaneous redox reaction is changed to electrical energy that can be used to do work. Now, as promised, here's my galvanic cell setup. It's essentially looks kind of like two beakers that are connected by a kind of like a glass throughway. And then that glass throughway has something called, it's got a little salt disc right there. We'll talk about that in just a second. So the two black rectangles, these are my electrodes. There's a wire going from my electrode on the left to my electrode on the right. That little black porous disc in between the two beakers, if you will, or the two compartments, is a salt bridge. And I always draw my anode on the left. Anode is where oxidation occurs. And then I always draw my cathode on the right. So the right-hand compartment is the cathode. The left-hand side compartment is my anode. So the anode is the electrode where oxidation occurs, oil, right? And then the cathode is the compartment or the electrode where the reduction occurs, and we use the phrase RIG, reduction is gain. Now, using the previous example, I would have my Fe2+ solution in my anode solution, and I would have my permanganate solution, MnO4-, would be in my right-hand compartment, my cathode compartment. So Fe2+ is my reducing agent. He's the one getting oxidized. My MnO4- solution is my oxidizing agent. He's in the cathode area where things get reduced. All right, so if you notice the electron flow, the electrons flow from anode to cathode. Okay, now how exactly does MnO4- get reduced? Does it just sit around and wait? Actually, it's a very active reduction. It gets reduced by pulling electrons towards itself from the other compartment. Okay, and we'll see plenty of these sketches of galvanic cells as we do plenty of sample problems in the videos to come for section 17. But I want to make some notes now on the galvanic cell that we just saw, the first galvanic cell of many that we just saw. It says the two beaker-like compartments are separated by a salt bridge. So all I did was label it in the sketch. I didn't tell you what it was. I think I mentioned porous disc, but I didn't tell you exactly what it does, what it's used for, okay? So how it completes the circuit. Example, salt bridge. A porous disc, in other words, a semi-permeable membrane. So it selectively allows certain ions to go through, certain stuff not to go through. Porous disc, semi-permeable membrane that permits ions to flow back and forth without allowing extensive mixing of the two compartments or the two solutions in each compartment. All right, so that's good. It's almost like we've got these two compartments separate, but at the same time we can selectively allow ions to flow back and forth as needed. All right, so that's the salt bridge. Wanted to make sure you had an idea of what that was. So let's also make some other notes about the galvanic cell. So we've got the salt bridge up there, which is a porous disc that permits ions to flow back and forth without allowing extensive mixing of the two solutions. So what are some of the other components or structural details of the galvanic cell? Well, the salt bridge, because I want to have a complete set of notes here with my 1, 2, and 3s, I'll just put the salt bridge in real quick. Salt bridge, it completes the electrical circuit. Okay, we don't want a dead battery, right? So the salt bridge completes the electrical circuit by balancing the charges in each compartment. Those compartments being my anode, which I draw on the left, and my cathode, which I draw on the right. All right, so that's number 1, salt bridge. It says here, without the salt bridge, electricity would not flow. In other words, without the salt bridge, electricity would not continuously flow. Eventually, you'd end up with something called a dead battery because we need our circuit to stay complete, right? So without it, electricity would not flow. In other words, electrons are not going to move from anode to cathode because there'd be no circuit and a buildup of negative charge at the cathode. All right, finally, number 2. Number 2 is galvanic cell. And I believe I mentioned this quickly on the last page of notes. I want to write it down here again under our notes about galvanic cell section. Galvanic cell. This is a device in which chemical energy from a spontaneous redox reaction is converted to electrical energy. Electrical energy, we haven't said yet how that's measured. It's measured with something called a voltmeter. So that would just tell you how many volts of electricity you are generating. All right, number 3 on our list of notes about the galvanic cell. It says other ions, and we can see the overall balanced redox reaction to see the other ions. For example, we had the 8H+, didn't we? So other ions besides the oxidizing agent and the reducing agent, those guys being MnO4- and Fe2+ respectively. The other ions are also present in the galvanic cell. Okay? They're present in the two compartments of the galvanic cell. All right, bullet point number 4 underneath our notes about the galvanic cell. The oxidizing agent, which in our example is MnO4-, the oxidizing agent gets reduced. How does it get reduced? Well, I mentioned this kind of verbally out loud a little bit earlier. Now we have it in our notes. It says the oxidizing agent, MnO4-, gets reduced by pulling electrons towards it from the reducing agent. So electrons, the reducing agent is in the anode compartment, and the oxidizing agent is in the cathode department. And so what's going on here is electrons are flowing from anode to cathode because the oxidizing agent is pulling or drawing or attracting those electrons to it from the reducing agent via the wire. Okay, and we can measure that pull using our voltmeter. So it says here, and it's got the little bullet point there for number 4. The pull or driving force of the electrons is called the cell potential. We'll be talking about cell potential a lot, over and over and over with every video. So cell potential has a little cursive E with the subscript cell. That is cell potential. It's also called electromotive force or EMF. I won't use it EMF in our notes. I use E cell. So E cell has units of volts. Now, we will kind of use volts mainly in our video series here for section 17 on electrochemistry, but there is some unit conversions at the end of section 17, so it is important to know that 1 volt is a joule per coulomb. Okay, 1 big J over 1 big C. 1 volt is a joule per coulomb. Now, in the next video, we're going to kind of hone in on sketching galvanic cells and calculating E cell. It's very important to know what the voltage is across a wire, because the voltage is measuring how much electrical output, how much electrical energy you've made that we can now use, direct it through a motor, and then use it to do useful work. Okay, so we'll talk about that in the next video, video number 2 for section 17. All right, so we'll see you right now for video number 2, section 17 coming up.